Hello everyone, and welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. Today's seminar is part of our NGSS at NSTA series, and it is titled Teaching NGSS in K-5, Constructing Explanations from Evidence. This evening, our presenters are Carla Zembel-Saul, Mary Starr, and Kathy Renfrew. My name is Sue Hokinen, and I will be moderating today's program. And with that, I'm going to give you a glimpse of our beautiful presenters. Okay? But before we formally introduce them, I want to give Ted Willard from NSTA an opportunity to introduce the next generation science standards. Ted?
Thanks very much, Sue, and thanks everyone for being here tonight. It's really exciting to have you all in place and spending some time during your summer to get more familiar with NGSS and with ways you can improve instruction in your classroom. Just a few quick pieces about NGSS. It was developed by 4 organizations: the National Academy of Sciences, Achieve, the American Association for the Advancement of Science, and of course my favorite, NSTA. There was a 2-step process in developing the standards. The first was the Academy developing the framework for K-12 science education. Then the standards were developed, and those standards impact all the different areas of instruction: curriculum, instruction, assessment, pre-service education, and professional learning. That first piece here, the framework, get a little bit of idea about that. I hope you're familiar with the framework, that you've seen it before. If you haven't, there's no excuse. You can get a free PDF from the National Academy's Press. You can also get a hard copy at the NSTA store. And the big idea here in the framework are these 3 dimensions: the scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. And I'll give you just a quick overview of what those 3 pieces are. The practices, these are things that students do, that scientists do, as engineers do. Things like asking questions, planning investigations, analyzing data, constructing explanation, engaging in argument from evidence. These are the ways we go about increasing our knowledge of the world around us and finding solutions to problems. The cross-cutting concepts are concepts that are not unique to any one particular discipline. It's not the purview of biology or chemistry or physics or geology, but that cut across all of those. Get it? Cross-cutting, cut across. Things like patterns, systems, structure, and function are examples of cross-cutting concepts. And then we have the disciplinary core ideas themselves: life science, physical science, earth and space science, and the standards also treat engineering and technology as a disciplinary core idea. And so all of those pieces play together in NGSS and are broken down into finer grains, and even into finer grains beyond that. Now, all of those pieces were described in the framework, and then the standards had to take those pieces and figure out how they all wove together. The standards themselves were developed by a consortium of 26 states, ones in blue here. There was no federal involvement in any of this. There wasn't even a single penny of federal dollars spent making the standards. There were, however, writers from all over the country as well. This represents the location of each of the 41 writers, about half of whom were actually classroom teachers at the time that they were working on the standards. As of this point, we have 13 states in the District of Columbia that have adopted the standards. We've also got a number of states that have developed their own standards, making use of the framework. And that means that over 30% of students in the United States live in a state that's adopted NGSS, and when you include those other states I just mentioned, it's more than 1/3 of students. Here's an example of a performance expectation from NGSS. This one says, construct an argument that plants and animals have internal and external structures that function to support survival, growth, behavior, and reproduction. And this is what we want students to be able to do at the end of instruction. But in doing that, that ultimately becomes a way to check and see that they have mastery of the practices, core ideas, and cross-cutting concepts. Because construct an argument is a practice. The idea that plants and animals have internal and external structures that function to support survival, growth, behavior, and reproduction. It represents this disciplinary core idea. And then the idea of internal and external structures that function is an idea that fits in the idea of systems and system models, and the idea that a system can be described in terms of its components and their interactions. And so this performance expectation goes and is a way to assess all of these pieces. It's important to keep in mind, though, that it's not meant to be a description of what you as a teacher have to do in the 4th grade classroom. You have a lot of different ways to play around this. So keep that in mind. We will now jump into the presentation, and I'm going to pass things to Carla, Mary, and Kathy, who are fantastic folks and have done some great workshops for us. Ladies?
Thanks, Ted, and happy summer, everyone. We're so glad to have you with us in this Northern Hemisphere summer evening. I just got back from New Zealand, so I'm very much realizing how hemicentric we are in North America. So just acknowledging that it's not summer everywhere in the world. My name is Carla Zembel-Fall, and I will be joining you tonight. I am joining you tonight from Madison, Wisconsin. I'm actually a professor and teacher educator at Penn State University, and I'm here working with some colleagues. I have very deep commitments to the connections between research and practice and work in school-university partnership settings. And I have recently co-authored with my colleague Kate McNeil and Kimber Hirschberger the book, What's Your Evidence?, which we'll be referring to off and on tonight. I know we have a diverse group, so I'm hoping that even if you're not an elementary school teacher or working with elementary school teachers, that there'll be something that you can take away with you. And with that, I'm going to hand it over to my wonderful co-presenters and outstanding colleagues to introduce themselves and get us started tonight.
Great. Hi, I'm Mary Starr. I am the Executive Director of the Michigan Math and Science Centers Network. We have 33 centers in Michigan, and we're really primarily responsible for teacher professional learning in science and mathematics throughout our state. I am also the co-author of a middle school set of curriculum materials called Project-Based Inquiry Science. And I'm totally thrilled to be able to meet with 153 of us this evening to talk about science in the middle of our hemisphere's summer. And in Michigan, it's a beautiful 78 degrees and sunny skies, so it's a great evening. And now I'll pass it off to Kathy.
Hi, everybody. My name's Kathy Renfrew, and I am currently the K-5 Science Coordinator for the Vermont Agency of Education. I'm also an NGS junkie, and I do lots of things with NSTA. I'm really enjoying tweeting. Some of you may recognize at KR Science Lady, and I love working with these ladies and learning as we go along too, and loving the collaboration, the opportunity to collaborate with you all. So thank you all for being here. And I'm going to advance the slide, and I'm going to give you a little bit of information about tonight's webinar. These are the big points that we want to do. We want to address 3D learning with an emphasis on cross-cutting concepts. We're going to introduce CER as one framework for constructing explanations from science. We hope to highlight the importance of engaging learners with phenomena, and this is really, really important. We want to demonstrate the KLEWS chart as an instructional strategy for making thinking visible and the development of scientific explanation. And we hope to have some opportunities to talk with you and to discuss science teaching. So we've told you a little bit about ourselves. Now can you tell us just a little bit about who you are? And
Okay.
moderators, could you put up the clip art so people could see?
I sure did. No, that's fine, Kathy. You guys should see your whiteboard tools now. Go ahead and grab the clip art, which again is the mountain with the sun coming over the top of it, and grab a piece of clip art and tell us how many years. If you haven't noticed, we've got two things we're looking at here. How many years of experience and where you are. And it says 5th grade teacher, but I would just say a K-5 teacher perhaps. So if you're teaching K-5, that would be the first column, and then other teacher would be on the side, and then of course your years of experience. To make sure that we're getting the 2-dimensional. We need the 3-dimensional though, right? This is awesome. Just let me know when you're ready for me to pause their toys or their tools. Again, I see some of you typing in the chat. If you do not have access to the clip art, please feel free to type that information into the chat. Tell us your years of experience in teaching and or in education, and then what role you have as an educator.
Look at this. This is amazing. Absolutely amazing. I'm going to give you just a couple more seconds to finish up this piece because we have a lot to share with you in a very short period of time.
It looks as if they're across the spectrum here.
Yep. Okay. This is the warning. Sue, go for it.
Okay, I'm going to close the clip art, taking away the tools.
And I am going to move on, but I want to thank you all for sharing because that does give us a sense of who's in the room and where, and maybe what you're thinking about as you're thinking about the change to NGSS. So I want to talk just for a second about the importance of being an engaged participant. The only way we know that you are enjoying or have questions is by your response to polls and by using the chat windows to share ideas. We really want to hear from you, so please ask us questions. There might be times when we don't have all the answers or we can't answer them in our time period right here, but we will get to you and get to your questions somehow. And something that's very important about webinars, presume positive intentions. The three of us are learners too. Even though we're going to share information with you, we, again, like I said, we're all learners in this room and we're here to collaborate.
Thanks, Kathy. I thought that was pretty impressive, too, the group that was able to turn out tonight. And I also applaud the administrators who are here. It means I'm guessing that you're trying to understand why science might be looking a little bit different in some of the classrooms that you're observing and working in. We are going to be sharing with you numerous resources tonight to support you wherever you are on that spectrum of experience and grade level that we talked about or that we shared earlier. There's lots of great research out there. This is one of the resources that you can go to. The STEM teaching tools, that's Bill Bell and his group of colleagues and teachers who are working on this, and what they do is take the research and translate that into briefs and tools and information that's accessible to school partners. And so just a couple things to point out here. One, all of these are based on the research, but it's really important to note that science content is best learned by engaging in the practices. That's really important, and it echoes what Ted was telling us about at the beginning about how the framework and NGSS were developed. Also building on prior knowledge and experience, we'll talk about that a little bit today, but a lot when it comes to the webinar next week. There's the notion that all children can learn ambitious science, three-dimensional science, which we'll be talking about tonight, and the notion of science, technology, and applications of science being central. So as we get started here, let me begin by asking you a question. So Kathy asked about what it is that you do. I want to hear a little bit about what you see. So there's some images from the classroom that we're going to have a video from a little bit later. This is a second grade classroom, and I'm really interested, so use the chat window here to type your thinking about what activities students are engaged in and why. And if you feel like it, sticking yourself out there, go ahead and add which aspects of these activities are familiar to you, or are there any that are foreign to you. So we have students using tools, observing phenomena, collaboration, hands-on, asking questions, discussion, research, notebooking, so someone has noticed that. People are noticing that technology is being used, recording data. Those are great. So hang on to that thinking. We're going to actually come right back to this in a few slides down the road. But one of the things that we're going to emphasize tonight is that, oh, I see hot plate in your hot plate, and then please notice the safety goggles because, yes, we were doing what was considered an activity that needed adult supervision and safety supports. So one of the big shifts that we're trying to make as we move towards the new vision for science learning that's put forth in the framework in NGSS, these shifts include the shift to 3D learning from a focus on just content. We're going to address that tonight. A shift from science topics to phenomena and driving questions, and a shift from activities, or what a good colleague of mine once called activity mania, to evidence-based explanations, and that's the focus for our entire webinar tonight. So and what that means is that we don't get rid of activities. Activities end up actually being very important to us when we're teaching, making the shift to NGSS, but what's important about it becomes different, and that's what we're going to focus on, one of the things that we'll focus on tonight. But Mary's going to take us through this first set of shifts from a focus on science content only in the past to now more of a focus on three-dimensional learning.
All right. Thanks, Carla. So what you've probably all heard about is this idea around three-dimensional learning. And as Carla pointed out, one of the things that we really want to do in this webinar is share some resources and build on the work of others. And that might be exactly the same kind of thing we want kids to be doing in science classrooms. So we're doing a little modeling maybe too. But you've probably heard about three-dimensional learning. And this comes from the framework for K-12 science education and is the way that the next generation science standards are built. And I've seen a lot of different ways of talking about this idea of three-dimensional learning and how it all works together. But I have to steal the quilt analogy borrow the quilt analogy from my colleague, Arthur Eisencraft. He uses the quilt to show the links and the connections between the three dimensions, the disciplinary core ideas, science and engineering practices, and the cross-cutting concepts. So we thought we would try to use that as an analogy for you tonight and see if that really rings for you and brings a little bit deeper understanding of how these three dimensions work together. So if you can remember what this quilt looks like at this moment on the screen, I'm going to take it apart now and dissect it into those three dimensions. So the first dimension is I think about them as these stars. And this is the disciplinary core ideas. And the disciplinary core ideas are not just every single piece of content that we've had kids using or memorizing or matching words to as we might have done in the past. But they're really the core ideas for every science, life, earth, and physical science. And the piece that I like the most about them and about thinking about them is this third bullet about how they connect societal or personal concerns. So those core ideas within life science, within earth science, and within the physical sciences that really are central to understanding how the world works and how those individual sciences work. So there's the stars, and then the next piece is this, these red sashing that connects those stars together. And those represent the science and engineering practices. And the practices really are consistent with the ideas around what it is that scientists do or engineers do when they're doing their work. And those have been highlighted in multiple documents, back again to the framework or to the NGSS documents, and you can find them there, descriptions of the practices there also. But these are the difference from the skills or science process skills that we have been using in the past. So we're moving past the idea that we want kids to measure or to be able to use a microscope into thinking about the social aspects and the cognitive aspects of science. So the science and engineering practices include all of these different ways of and tools of science, and the specifically around what it is that scientists use and do while they're doing the work of being a scientist or being an engineer. One of the important features of the science and engineering practices is that in NGSS and in the framework, we've really made it clear that engineering is a part of this, and that scientists and engineers use these practices in different ways, and that we formalize the idea that engineering has a place in K-12 science education. And then there's this last bit, so the blue section that is representing the cross-cutting concepts. And these cross-cutting concepts are the themes of science, as you might remember they were similarly called in Project 2061, are really the ways that that science is linked together across those domains. So the disciplinary core ideas were broken into life, earth, and physical science domains. And the cross-cutting concepts are those ideas that stretch across all those three separate parts of science. So the cross-cutting concepts have become more formalized now. And the expectation is that students will make use of these cross-cutting concepts in their science learning. I'm thinking, the way I'm thinking about it at the moment is as lenses. So if you think about the lens of patterns, how would students see the world as one of the lenses they're using in a particular time is patterns, or as we're going to talk about in a little bit, cause and effect. So when you think back about it and you put those three pieces, the three dimensions back together, you get this quilt. And pieces of the quilt are not nearly as useful or beautiful when they're separated from each other. But when they come together, then we really start to see that idea about three-dimensional learning. When we're focused on three-dimensional learning, we're really shifting science instruction. And we're developing those learning environments now where students are responsible for exploring, examining, and explaining phenomena. It's really about the phenomenon that they're looking at, or the designing solutions and those big ideas that they're trying to explain. These are the critical pieces of the NGSS and the framework, and the difference between those parts being separated, the three dimensions being used separately, and now then they're being used together in instruction. So what we were focused on today is the structure and properties of matter. And we're really looking at this one disciplinary core idea and how this core idea might be used. And we're using a second grade example because we have to use some sort of an example. And it's really nice to start thinking about the core ideas in the early grade levels. But there's applications of this throughout, including in 5th grade and then into the high school, middle school and high school. So in the core idea for structure and properties of matter, students are thinking about different kinds of matter and how they exist and how heating and cooling might change those properties. This is the learning progression. So one of the key ideas around the framework for K-12 science education is that the core ideas would build on each other. And so you can see that there's the second grade structure and properties of matter, but then that again is revisited in 5th grade and then in a more sophisticated level in the middle school and the high school. All right, Kathy, it's your turn.
So one of the things that I know personally, and from the many conversations I've had with teachers, and I know that Carla and Mary have also had with teachers, is that elementary teachers, including myself, and my hand again is raised, are often uncomfortable sometimes with their own content knowledge, and I personally had to change that and go back and make some and do some more learning on my own. So we know that this is the case in many elementary schools, and it's understandable because elementary teachers are often expected to know and do everything, and that's very hard. So I was just curious, in this particular group, are there elementary teachers who also are struggling a little bit with understanding the content and the DCIs of the Next Generation Science? And if you feel comfortable, please just share that in the window. And I'm going to share some resources to help you so that you know that there are places to go, because that was one of the hardest things for me, is knowing where to go. So right here we have an physics ebook, and it has built-in investigations and simulations, lots of reviews. It's a great place to start. Again, to really understand a little bit more, you can go to the Achieve website, which is where there is lots of material around the area of the Next Generation Science Standards. And of course the Bible, the framework. I can't even tell you how many times a day I go to this document. And because I have to clarify for myself some of those concepts. So that's another one. And just before we move on a little bit for the framework, I just wanted to say that another excellent site, as we'll talk about more, is the Next Generation Science Standards, NGSS, at NSTA, which is the hub. And many of the resources that are available on the Achieve website are also available on NSTA, and also with a little bit more. Okay, so to change gears a little bit here, one of the things that we know is really important is that it's really important to focus on the ideas of our students. There are no blank slates. Students come to us with lots of ideas, ideas they've got from their everyday lives, and different things that they've been able to do, and all of that information helps determine and shape what their learning is going to continue to be. And we know that assessing learners' prior knowledge is critical, and it's critical to crafting good instructional experiences for our students. And we know this, and we are going to really spend a lot of time on this in our next web seminar, because we don't have as much time to do this, but we aren't leaving this. We just want to give you one more step in the sequence of things that would be also considered when building and constructing an explanation. And Mary?
All right. So what we're trying to do in this web seminar is to introduce some ideas, go a little bit deeper in them, show you them again. So we're going to have this, it's going to be scaffolded over the time. So you're going to see little parts of things, and hopefully it's our plan that that scaffolding will support you in really understanding the purposes of the webinar. So what we're talking about, what we're really pushing on, is moving away from what Carla talked about earlier, activity mania, and getting students involved in doing a lot of stuff or being busy, which, you know, honestly, it's what we thought was supposed to be happening in science classrooms. It was at least a step better than just reading from a book. And now we've learned a lot through watching classrooms, from talking with kids, from learning more about how learning happens. And we know that what we want kids to be doing is building explanations about phenomena, about the things that they experience in their world. And when we do that, then we're actually taking those observations that we were having kids make and leveraging those along with their data to create explanations. And one of the ways that we'll talk about creating explanations or having students share their explanations is through a framework that you've probably heard of called Claims Evidence Reasoning, or a lot of people call it CER. So the CER framework is one way that you might have your students provide explanations or create their explanations. So you'll see this graphic again. We'll show it to you a couple of times. The real critical part right now is over on the left-hand side, where students are creating their claims based on evidence. So all of the ideas that they use in order to make a claim about why phenomenon happens have to be supported by evidence. And this is the critical piece of the CER framework that starts to move us past that idea that just being engaged in an activity is going to be enough. So I got a question for you. If our topic for tonight is structure and properties of matter, and we're really going to focus a little bit, keep it a little tight on students in K-2, so a little bit younger students. What phenomena do you think that students might investigate if what they're trying to think about is structure and properties of matter? So if you could add your ideas to the window. So there's about 1 million ideas. Has everyone done at least one? Because it looks like we've got evaporation, solids, liquid, gases, very common, surface tension, density ideas, so thinking and floating with little kids, different types of matter, so slime has come up a couple of times, phase changes, melting, and boiling. All right. So all I needed was one person to help us move our discussion along, and about 25 people said melting or boiling. So what if the three-dimensional learning included exploration, examination, and explanation of how solids and liquids change depending on temperature? So that would be consistent with the disciplinary core ideas. And we would then use the three-dimensional learning, the practices, and the cross-cutting concepts to help students explore, examine, and explain how solids and liquids change depending on the temperature. So we're going to be able to watch a little bit of video and share our ideas, and Carla's going to take us all on now.
Thanks, Mary. Good. My subliminal message from the beginning worked, right? So there were lots of pictures of melting. Some of you talked about melting. when you have this focus on evidence-based explanations, we're just going to shift that activity of melting, doing the melting activities that we often do in elementary classrooms, to one where a lot of you, if you recall from when I showed you these pictures initially, and you were writing in the chat window, you were focused very much on observations, making observations. I saw that over and over again. And we are going to, in an explanation framework, start to treat those observations as data, something that you do something with. So we're going to leverage those observations as qualitative data. It's also possible to have quantitative data, but here, for example, what you can see is that kids are actually doing drawings and writing and talking about their drawings. So when we're doing this, the notion is that hands-on activity alone, it's just not enough. So what we are trying to do and what Mary was setting up is this integration of three-dimensional learning. We still use activities, but they're intentionally selected and sequenced to provide opportunities for data collection. What usually happens, and this happened in my own teaching early on, as well as many of the pre-service and practicing elementary teachers that I work with, is that they were really good at doing hands-on activities. They know that kids were motivated and wanted to do them and were excited about them. But then what would happen is that they would all come together, sit on the carpet, and talk about their observations, their data, what they saw. They very rarely got to that place where they pushed into how do we take those observations and construct arguments and explanations using those observations as data. So that's what we're going to shift to tonight, and that's the intention of the video that we're going to share from you from classroom teaching in just a moment. But when we look at this, it's really important. So if you come over here and you look, let me see. I'm going to grab a star because I like that too, Sue. So if you look over here, what you'll notice is that activities are still a part of a storyline about properties of matter and changes in matter, and that the part that we're going to look at tonight is only one small piece of a much larger content storyline. So as we talk about the teaching, you're going to have to think about the fact that there were things that happened before, and there are things that happened after the part that you're going to see. And all of those things include activities, but we're using activities in a slightly different way. So I'll ask you to watch for that. So at this point, you've identified the topic, you've learned a little bit more about where you're headed with that, you've shifted to thinking about phenomena, you as a teacher have made sure that you understand the content and that you know what kids understand, so there's a lot going on there, but now you have to figure out, how do I create a question that actually drives the investigation that kids are going to make these observations, engage in these activities, collect data about. And surprisingly, a lot of the teachers I work with, and in my own teaching when I try and do this, this is actually a really hard thing to pull off. So some of the challenges that we have noticed in the field are that if your question is too vague, it's very difficult to answer with the CER or the explanation framework that we're going to share. It can be if your question is too broad or too narrow, that also constrains. So a lot of times when teachers begin to feel comfortable with teaching in the ways that we'll talk about a little bit more, share with you tonight, is that the kids start to figure out that the claims that they're trying to generate don't necessarily match the question. So that leads to interesting conversations of, do we have the right question about the phenomena, or do we need to go back and collect different kind of data to be able to answer that? So you kind of have to think about this question as being really important to frame up the investigation, because the investigation, and when you collect those data, you can move backwards into experimental design, or you can move forwards with the data and look at patterns and construct claims. So this ends up being really important, and we'll share some examples in the next couple of slides. For those of you who are in adoption states, just to take a look at this slide really quickly, the performance expectation, Ted talked about these earlier in the presentation. The idea is that this, it actually integrates and articulates three-dimensional learning, and it is the end point that the entire storyline that the teacher is working on is building towards. So if we look at that a little closer, I find that, again, that you can see very clearly the integration of three dimensions. In particular here, construct an argument with evidence is a practice, a scientific practice, and our DCI is really well articulated here. But the clarification statements are also really helpful. So it kind of gives you examples that are age appropriate and ideas for the kinds of investigations that you might do in the classroom. So they're necessarily integrated. So even if you don't adopt NGSS, this can be a really helpful tool, the performance expectations, for organizing your curriculum and your instructional practices. So we're getting into the point at which we're going to view a video. This video was done in November of 2014, taken in central rural Pennsylvania, which is where I live, close to Penn State University in the local school district. This is a recent graduate of our program at Penn State from 2009. Her class last year consisted of 24 students, 3 with IEPs and 4 ESL students. So I realize this is not an urban center, but drive out of town 5 or 10 minutes in any direction and you will be on a dairy farm or in a state park. So we are what we refer to fondly as centrally isolated. Video is edited down from, I call it a 90-minute lesson. It's a 90-minute lesson that's spanned across multiple days. So you know if you're an elementary teacher, you have lots of other things to do in your day. We'll be talking about integration in the future. And I always put this note on here about respect for colleagues who share their classrooms with us. I think it is incredibly courageous and brave to open up your classroom so that other professional educators can learn from you. So again, going back to Kathy's comments, it's really important to assume good intentions with this teacher. None of us is perfect, and we're all really working towards the vision that's laid out in the framework in NGSS. So before this lesson, it's important to know that the teacher did assess prior knowledge of students. They looked at the characteristics and have a language for talking about solids and liquids and their properties. And the kids are making and have made predictions about what happens to solids, and they found solids in their classroom, what would happen to those solids in the presence of a heat source. And so with that, I'm going to have Sue help us push out the video. I'll warn you that if you've set your audio to be comfortable to listening to this webinar, it may be a little loud to you at first, so have your trigger finger on the volume button so that you can tone it down if it comes across as too loud. Sue?
Thank you, Carla. And in just a minute, I'm going to go ahead and push this video out. And what that means is that a separate browser is going to open, separate browser window is going to open. You may have to click play in order for the video to begin. However, when you are done watching the video, and we'll give you plenty of time to watch the video, when you're done watching the video, you can, I like to leave the windows open. That way I have access to the video to review it again at a later time. But I encourage you to come back into the web seminar and give us a green check. And you'll see the check mark is at the polling button where we saw the A before. It's right underneath your name at the very top where it says participant. Give us a green check when you're back in the room, and that'll let us know that we're ready to proceed. I'm also going to post the link, and I'll post it now for the video here in the chat, so if for some reason it doesn't open, that you will have access to it there. So let's go ahead and hopefully find where I'm going to do this. Here we go. And in just a second, your browser should open. And I'm going to silence my mic so you can hear.
Carla, please click on your talk button.
I just skipped ahead a couple of slides, so as you're returning after watching the video, there is a discussion question that is about the experiences and how they might help students explain the phenomena of melting. So if you can put that, your responses to that and other things that you're noticing in the chat window, we'll talk a little bit about that next. So I see people noticing the agree, disagree language, observing and listening, that there's an appreciation for what the teacher's trying to do here with the students, sharing vocabulary building, really pushing, we call it the press, really pressing for kids to talk about their evidence and notice patterns in the evidence that can help them explain the phenomena. And we'll get back to that, how that fits with the CER framework in just a couple minutes, but that press is so important. So I saw someone referring to it as leading questions. We really talk about what the teacher's doing, the talk moves that she's using, the questions, as being really important to getting kids to start to develop a classroom culture in which they notice or in which they know what their role is, like the agree-disagree language, like looking for evidence or knowing that they have to, establishing the norm where they have to set up their claim or their contribution by also not setting it up rather, but backing it up with evidence. Any other collaborators want to jump in on that, on the video really quickly before we move on?
This is Mary.
This is Kathy.
Oh, go ahead, Kathy.
Go ahead, Mary.
Hey, Kathy, if
I'll
you could
go.
shut down your mic. Yeah, okay, so if you're going, Kath, that's fine. Just one mic open at a time, please. Thank you. And I'm going to call it, and I'm going to say, Kathy, you go.
Okay. Thank you, Sue. One of the things I really noticed was something that Carla mentioned, was that pressing and that the intentional asking of particular questions to really get students to answer. The teacher wasn't satisfied with just so it's melting. Well, what do you mean it's melting? And pressing for further evidence of what was going on. And now I'm handing it to Mary.
Okay, thanks, Kathy. We probably should get our act together there. Carla pointed out, and you all have made really good observations about that video and the teacher's use of language, and more importantly, the student's use of language within the video. And I want to just impress on everyone that this is very intentional and planful, like Kathy was saying, and it doesn't just happen. It's really hard work, and you all know that, but it's also a little bit of a path of we have to work on it a little at a time, and we have to accept that sometimes this kind of level of conversation isn't going to happen in the classroom. And that doesn't mean we stop. We keep going back to it and trying again and finding other examples and scripts and video examples like Carla's showing us. So it's challenging. And so sometimes when we hit that challenge and the students hit the challenge of talking to each other, it's easier to fall back into our other habits and harder for us to press on, knowing that this is the most important way for students to learn, and helping them to see that their learning becomes richer when they engage in this kind of social interactions is also really important. Thanks, Kathy. Thanks, Carla.
Why don't you take it, just keep on going, Mary. I think the next slide allows you to build on how the three-dimensional learning played out in this particular example.
All right, so I mentioned before we're going to come back around and look at these ideas over and over again in a more scaffolded way. So this is the disciplinary core idea for this piece around structure and properties of matter. So the topic is about structure and properties of matter, and we were looking specifically at the phenomenon of melting. And so the disciplinary core idea says that heating and cooling a substance may cause changes that can be observed. So we watched as the students observed how heating might change a substance, and that sometimes these changes are reversible and sometimes they're not. And we're going to be able to think about through those activities and through the storyline how we might get that piece about the reversibility in. Several of the comments earlier were around plasma and how cool plasma is as thinking about properties of matter. And in the performance expectations, it's really important to pay attention to the assessment boundaries and the clarification statements. And so plasma probably isn't within the 2nd or 5th grade disciplinary core ideas and the assessment boundaries. It doesn't mean it's not cool and that you can't teach it. The question is how you're going to get the phenomenon that kids will be able to experience. So that's a challenge. As I was reading the comments, I was trying to think about where's that phenomenon going to come in for 7- and 8-year-olds. And you probably noticed in the video the students using several science and engineering practices. So they were asking questions, they had carried out their investigation, they had collected that observational data, and they were using it then to begin to develop their explanations. So it's within the second dimension, the science and engineering practices, where they're using and becoming fluent with the tools of science. And then the cross-cutting concept, or the blue part with the squares or the diamonds in it. So in these experiences that we were looking at, we were specifically thinking about the cross-cutting concept of cause and effect, and how does that cross-cutting concept play out in what the teacher had planned for the students and in their experiences. It's not necessary to focus on 7 cross-cutting concepts within a storyline. It's more beneficial to be formal about 1, maybe 2 cross-cutting concepts within any one learning experience. So in this one, the cause and effect seem to be the most obvious cross-cutting concept. The cause, when temperature changes, the effect, and then the effect of melting. So if you look at the storyline, we have examples of that cause and effect within the storyline, where intentionally that's been built in to the plan so that students will be able to use that lens of cause and effect when they're thinking about their investigations and exploring the phenomenon. So as we approach this webinar, Kathy, Carla, and I were really thinking about, well then, how do we look for cause and effect in what kids might say? How do we really make sure that in their formal discussions, they're thinking on using that lens of cause and effect in their explanation? So we started to really sort of throw around some ideas. And we think that in the past, this blue text would be something that we would have thought about kids saying, right? I held the chocolate in my hand and it melted. So it sounds a little like there's some cause and effect happening there. I did this and then this is what happened. But we think that we're going to push a little bit harder and make this cause and effect connection more formal with the students, more explicit. So we were thinking that one option, there are certainly others, would be to push kids to use more clarity in their language. And perhaps one example might be, I held the chocolate in my hand, and because my hand is warm, so the real cause is that warmth of your hand, the effect is that the chocolate melted. And when we think about the language that students are using, and we really want to make formal and explicit these cross-cutting concepts, Kathy, Carla, and I were really thinking about how do we get that in the students' language in a way that helps them to use those lenses in multiple ways. So it's not just for this activity or for this set of activities that we want to see them use cause and effect, but we want them to be able to use that flexibly, that cross-cutting concepts in other storylines, in other experiences. Carla?
Thanks. Well, we intentionally, like Mary said, wanted to spend a little bit of time talking about cross-cutting concepts because of the three dimensions, they're the ones that are typically neglected. But now the idea is to pull together the example from teaching, the discussion that we've had so far, and what the group has been talking about to make sure that we get to this notion of how does this all work together for constructing explanations from evidence. So we mentioned, Mary mentioned earlier that the framework that we tend to use in our work in elementary schools, there are other frameworks and other models, but we use the claims, evidence, reasoning, and rebuttal work, the CER framework, originally developed by McNeil and Krajcik, but we have modified that a little bit and continue to use that with elementary with great success. The idea here is that you have the phenomena and the question that we talked about, and the claim is actually used to answer that question. Scientific evidence, evidence that is in the form of observations or data, other forms of data, quantitative data that are measurements that have been developed, actually have to back up that claim. The claim comes from that evidence. And then we have reasoning and rebuttal. And what I find is that it's much easier to show this in context than to talk about it. So let me share this diagram again because I really, and this is this diagram we also use in Kate McNeil's book that we did together, the What's Your Evidence book with elementary examples, and the McNeil and Krajcik book is actually middle level, 5-8 examples, or a 5-8 focus. But the idea here is that the evidence itself is used to construct the claim, and claims are debated on the basis of reasoning and sometimes evidence. But we always start with phenomena. We always start with that question that's under investigation. So let's take a look at what the kids were investigating, and let's build a CER sequence, a claim, evidence, reasoning sequence that's based on that. I see there's some excellent discussion in the chat window about what it might sound like. And remember, these are second graders, so try and keep that in your mind. We use Kid Talk to do this as much as possible, but this is actually what the kids generated. So they were looking at how solids and liquids respond to the presence of a heat source. That's kind of the question that they came up with to investigate the phenomena of melting. So the kids are saying, and you can kind of hear it, we put the pie pan with the crayons on the burner, they melted into a liquid. When we removed them from the heat, they turned back into a solid. They go on and investigate that even more. This happened with the chocolate and the butter and the ice, but the ice didn't change back. And so I put evidence first, even though claim, evidence, reasoning starts with the claim, so it makes a nice acronym, but the claim comes out of the evidence. So usually that first sharing where kids are sitting around and talking with one another, we're talking about the evidence. And as the kids share their evidence and discuss it and compare it to one another, they're looking for patterns. So eventually they can get from this evidence to this claim. Some solids change. Remember, she said, did we test all? The teacher, Colleen McCracken, said, did we test all of the solids in the world? No, we didn't test all the solids in the world, but the solids that we tested, they changed when heat is added, and when the source of heat is removed, some of those materials changed back to a solid, and that's based on the evidence. And here, the reasoning is, I pulled the reasoning from the framework. So this notion of heating and cooling can cause some changes, some substances, changes in substances that are reversible and others that are not. That's sort of the underlying explanation here. We're not getting to heat energy and temperature yet. If you looked at that continuum, that learning progression over time, you'll see that students eventually get to making those kinds of connections and when they better understand the particulate nature of matter. And then one thing that I really liked about this is that kids start asking about other stuff, right? In the context of an investigation that kids are doing that you might plan for them, they often come up with other things that you could try. And so what we're really trying to do in this process is honor those wonderings in a way that you can then, how hard would it be to test that? A lot of us have access to a freezer in the an all-purpose room or in the kitchen at our schools, the cafeteria. So what could we test that would allow kids then to have more ownership over the investigation? It's still a testable question, and it's still related to the phenomena under investigation. And this slide is intended to point out even more explicitly that what is embedded in the very nature of this question is a particular cross-cutting concept about cause and effect. And we really want to make sure that that cause and effect is in there so that we know it's there so that we can help kids make the cause and effect explicit in instruction and in their own sense-making about the phenomena. So back to this, the third webinar that we're going to do in this series the first week in August is very much focused on how do you build a content storyline. I put this slide back up. I find it really useful to again focus us on the fact that there is this one strand that we're looking at. This is one CER sequence. You have to have the question and the phenomena under investigation, and you have to use those activities investigations. When you're building an explanation, you need multiple CER sequences usually to be able to fully explain at the appropriate level, get the kids to co-construct the explanation for the phenomena that's being investigated. So all of this ends up working together. But when you're new at it, we find it really, really helpful to just start with one CER, and here it is. That's why we organize our table in this way. One CER sequence to help you get the hang of it, and then you can start putting sequences together intentionally to scaffold students' explanation construction. So we wanted to introduce you to one tool that we use regularly, and you could see it in the background. I think someone mentioned that in the chat window, that there's sort of a table in there and you know, what's on that. So can I just get a wave or a thumbs up if you already are familiar with KLEWS charts? KLEWS, KLEWS charts.
I actually have the polling button open, so you can give us a green check if you're familiar, and if you're not familiar, give us your red X.
Thank you, Phil. So far, we're looking to be half and half. Okay, a lot of people not. All right, so let me just explain, because one of the reasons that I really like this tool is that it maps really nicely to the practices, allows you to document students' explanation construction over time, and have a record in the classroom that you can keep coming back to with kids as you build these larger explanations for phenomena. So with the CLEWS chart approach, this is something my colleague and teacher collaborator, Kimber Hirschberger, and I started working on long before NGSS came around. But the focus here in the CLEWS chart was a modification of the KWL. If you're an elementary teacher, most people know the KWL chart, and we did that because we thought we could play off of something that was familiar to people, but what we found out in the end is sometimes what we did to make it familiar, it also makes it more confusing. So let me try and walk you through this really briefly. Initially, the focus is on what, with the kids, assessing prior knowledge, what we think we know. And we're going to spend a lot of time on beginning ideas, prior knowledge, as well as student learning, or student thinking and ideas in the webinar next week. So there are 3 in this series. Tonight is explanation, building, and tools associated with that. Next time is kids' ideas and thinking and how that relates, and meaning making and discourse. And then the 3rd one is on building a storyline. So we're really going to focus more here next week. The L in the E has the same problem that the C in the E in CER has, is that the evidence actually comes first. You have your phenomena and your question that you're investigating, you make observations, record data, and then you come up with the claim. So a lot of times people comment that that feels out of order. If you're trying to spell clues, it's out of order. If you're trying to explanation build, if you're trying to spell clues, it's in order, and if you're trying to build explanations, it's out of order. The wonderings are also honored here because a lot of times those end up being testable questions. And then the S is sort of the scientific reasoning, the science ideas that you might not be able to discover or observe in the classroom, but that are important to constructing the explanation. So here's an example of a CLEWS chart. This one is actually from Simple Machines. So what you can see is that the teacher, they're looking at multiple claims over time to build these explanations about Simple Machines, and so the teacher has actually included the questions in the, that are under investigation, and then the claim that answers that question right underneath it, so under the learning. But all of those, you can see she's used an arrow that links to evidence. I get putting the arrow this way, but you could also think about putting the arrow in the other direction like the CER framework does. And then as questions come up in real time, teachers are documenting those and pursuing those as is appropriate. And sometimes it's just running another set of investigations using the same materials that you already have. And then things like a definition for force or definition for gravity may not be something that 3rd graders in this case would come up with, but kids look at a lot of different sources and figure out how they're going to use these words to further enhance their explanations. And I really like it because, again, you end up with testable questions. Kids are saying things like it's hard when you heat it up. Can we change it back? And so I would say that's a great question. So we have come full circle, and now kids are asking questions that we can actually test. So the CLEWS chart is a nice tool for doing that. If you get the NSTA journal, Science and Children, the February issue in 2015 has a lot of examples and has an article about CLEWS and grade-relevant examples. So with that, I'm handing it back to Kathy, and we're going to bring you home tonight and get Ted going on time here, I hope.
So I just want to review a little bit about all of the information that you've heard tonight. And I know it's been a lot of information and a lot to try to absorb all at once. But the really important messages that we would like you to take from here is that we're going from just memorizing facts and science content to 3-dimensional learning. We've gone from facts to the big ideas, from skills to the science and engineering practices, and from the discrete, isolated pieces to connected. It's really important that our science instruction makes sense to kids. So if we can work to make our science instruction have context, think about relevancy, it's going to all be better in terms of student learning. Thinking about phenomena. Phenomena and driving questions are so very important to science instruction. This is probably the greatest aha I have had and continue to have as I continue to work with teachers and others to develop NGS instruction. And the last part that Carla and Mary and many of us have been talking about is we have to move away from activity and mania, from where we did an activity as an isolated event. All of our activities need to be real learning experiences for our students. And we do that by really thinking about how we lay them out with our phenomena, our questions, and as you saw in that storyline, it wasn't just one question, it was multiple. And we talked about today just one piece of that, the piece about the melting. Coherent sequence of learning opportunities for our students, so very important. I couldn't leave here tonight without talking about one of my favorite places for resources and a place where that's near and dear to my heart, as I'm also one of these people here, the online advisors, which is very exciting for me. But there are so many resources here, and I also think you will find lots of people to collaborate with and have discussions with if you spend some time exploring the Learning Center. And again, here are some more resources. Each and every one of these resources I put in the collection so that you would be able to reach them, access them at your own convenience. We've mentioned my Bible, the framework, What's Your Evidence, another one of my favorites, NGSS at NSTA, the Hub, a place that I spend a lot of time these days. We talked about STEM teaching tools, and another resource that I included is Writing in Science and Action, and it's by Betsy Fulweiler. And there's some different pieces when we're thinking about helping our students do some writing in science, and I just wanted to share the resources that are available. So, are you interested in continuing these conversations? Mary and I are going to start an elementary NGSS Twitter chat, and it's going to start on August 23rd. We're going to do it on the same schedule as the NGSS chat, the regular one. It's going to start 8 p.m. instead, and will be followed at 9 p.m. by the regular NGSS chat. And we will be using this hashtag, which is right here, ELN NGSS chat. So we really hope you join us. Mary and I like to Twitter. Professional learning. I want to spend just a minute to see what is one idea that you think that you got from us tonight. We hope you got lots. But what if you can think about one thing that you will take back to your instructional setting and use? We'd really like to hear about it. So would you please write that in the chat now? Thanks. Looking, the CLEWS chart and CER are winners. I'm going to move the slide ahead, but you can continue writing. And just a little bit of an advertisement for next Wednesday evening. We will be thinking about making meaning through discourse. One of the things that we heard from teachers and participants from our last web seminar series last fall and winter is that people really wanted more information about discourse. As I mentioned to you today, though, we will be also still having a connection to the work we did here tonight in constructing explanations. But we will really spend some time on this too, also as Carla mentioned earlier, really thinking about what students know when they come to this science instruction and how we identify what they know, and then what do we do with that information. So all of these will be part of our next week's webinar, and we hope to see you there. And I think this is where I hand it back to Ted, but I'm going to say thank you to my colleagues, seeing as I'm on this slide. So.
Absolutely. Thanks to all of you. We've got some time for some questions here. Pieces. I'm going to start sort of pull from some of the earlier pieces to begin with, but if you have questions, please go and post them up in the chat window. This is our chance for us to do that. We still have quite a good chunk of time to do so. I want to start with, there was some discussion in the chat room about hypotheses and how does that fit or not fit into the KLEWS process or the claim evidence reasoning process. Which one of you wants to try to take that? Carla, maybe?
Sure. I think it's a really essential vehicle for a couple of reasons. And so we usually talk about it at the beginning of a unit as one of the ways, so we talk about it as a prediction rather than a hypothesis, because usually kids are, at the beginning, when a teacher is using that to assess prior knowledge and get the whole process started, it serves a really interesting purpose. It actually helps the teacher make thinking visible and get all of the diverse ideas on the table, and the kids are making a commitment to a particular prediction, and they also see the diversity of ideas. So when they go into an investigation, it's not like we all already are assumed to think the same thing. So it kickstarts the process. You make that prediction, and then you begin to investigate it. And so when you're investigating, you're trying to figure out, we often start with, well, how did that work out with your prediction? And how do you know? So was that prediction supported or not? And how did that compare to your neighbor or your neighbor's group? So that initial prediction is important for so many reasons, especially as it relates to student thinking and the investigation process. When we come back at it at the end, so once kids have been through a CER sequence and they have their own wonderings and now they're going to go make predictions again, this is where I would call it a more educated guess or hypothesis, because now they are working from the set of observations that they've already had and trying to, loop that back around using what they already know. Now what can we do? So actually for next week, when we're focusing on making predictions and their role in sense making and in classroom discourse and as a formative assessment, we've actually intentionally selected a video that shows a teacher using those initial predictions and looping through 2 cycles where the kids are testing their prediction, coming up with a tentative claim, and then testing it again in a different context and building on that. So we hope that you'll join us, because I think we'll be spending a whole lot more time listening to kid talk, looking at kid writing, and talking about that role of hypothesis and prior knowledge.
Great, thank you. I think that was a great explanation. I just want to double check, Mary or Kathy, I don't think you need to say any more, but if you want to, jump in for a second. Otherwise, I'll go on to another question. Okay, great. We've got some people who are talking about, and I've lost the piece here as it scrolled through, but was talking about how monitoring individual instruction and the individual accountability is a really important thing for a teacher to be tracking all of their students. And how should they best go about this with the techniques that you're talking about today, which may be, some of which are, I think, more of a class-wide approach in some of the pieces here. So maybe Mary, is that something you would like to touch on?
Ted, I'm just going to apologize. I was reading the chat window. I have no idea what you asked me. I'm so sorry.
That's all right. we're dealing with individual accountability and the issue of how do we manage to keep account of how individual students are doing in our classroom as we go through and use some of the techniques that have been talked about today.
So when we use writing scientific explanations, there's a couple things that I wanted to make sure that we point out. That this really should be an iterative process. So a lot of people were mentioning in the chat window that they use the CER at the conclusion of the learning. But we often will have students write tentative explanations as the CLEWS chart and as what Carla's been talking about, and then update those explanations based on for additional investigations that they might do. So when they get to the wonderings piece, then they move on to another investigation, and then they can go back and update their explanation based on the new or additional evidence. It's in those times that we use the CER format or a scientific explanation format and ask students to make their adjustments or iterations, update their explanation individually. And those would be good opportunities for teachers to look at student work and to think about how the individual students are changing, ideas are changing prior to the small group or whole group discussion. So I think it's really critical to build in those places where kids, students are giving their individual ideas. One is clearly it's an instructional necessity. People are looking for opportunities to give students grades. That's real world. But most importantly, to be able to identify how students' ideas are changing and whether they're on the right track towards a more scientifically accurate idea. We do the same thing with the CLEWS chart. So students might, in that learning and evidence column particularly, they might write a learning claim and the evidence to support it individually, and then in small groups share those, and then in the large group share it and have it documented publicly. So there's really opportunities for that individual work to be used as assessment, either as a formative assessment for learning or as a assessment for a grade.
Great, thank you, Mary. So Kathy, I was going to throw this next question to you. Michael Masad asked about flipped classroom models and wondering whether in a flipped classroom approach, whether that fits into the CER model that has been discussed today.
I guess, first of all, I don't know a whole lot about flipped classrooms, but I'm thinking that it's really important that students have the opportunity to engage in investigations, to engage in predictions and investigations, and to develop those claims and find that evidence and go through that iterative process that Mary was talking about together. I think that there might be some ways of integrating the technology. One of the thoughts that just has come to my mind is that, using apps like Padlet, maybe when students are thinking about their initial ideas, which we'll talk about more, they might use the iPads and send that information to you, the teacher, through Padlet. But I'm thinking that most of what we've been talking about tonight is more face-to-face learning, and I'm going to yell out to my to see if they have anything to share.
Well, I can just add really quickly. I know some people really need the surveys, but we tried to talk about how we might flip this learning experience for you in the webinar by having you do some stuff before you came, maybe watch the video or read a little bit of, maybe read the KLEWS article or something, so we could actually engage in more discussion during the time that we have together, which is very precious. So we couldn't figure out how to do that in ways where the playing field was level, because we knew that there would be a lot of people who wouldn't be able to get to do the pre-homework before the webinar. But it's an interesting idea. I don't know that there's evidence to support it in relation to CER Framework, but I could see maybe having kids, if they had access to the kinds of resources that they would need to either try like an investigation that you might do at home, or watch some videos or simulation online, and then come and bring that understanding to bear when they're investigating the phenomena hands-on. But I really think that you're right, it's discourse rich. You need to spend the time talking with kids and co-constructing, but those hands-on, those common experiences engaging with the phenomena are essential to leveling the playing field in the classroom. But interesting ideas. I'd love to talk more about flip classrooms sometime. But Ted, I know you're chomping at the bit to get your part done, so I'm handing it over.
Great, thanks. And so we're going to take a moment here, just give you a few ideas of other places you can get some information. We'll then get you the survey pieces here, and we can stay around a little bit after the survey if other people have a few other questions to ask. But I want to start off with the aspect that you can find lots of the things you need to know about the standards, nextgenscience.org is the official standards site, and also I'm very particular to the NSTA hub, and you can find at that URL. There's discussions continually going on. There's an NGSS discussion forum in the Learning Center, and there's also a NGSS listserv for NSTA members that you're welcome to join into. We've done our coherent storyline here today, but we've got upcoming web seminars this summer on making meaning through discourse and planning the coherent. Oops, that's not the title of the last one. That's an error on my slide. I'm sorry. That's not. But we've got a third piece, which somebody else will type in what the title of the third piece is, because I'm forgetting off the top of my head. We've got some other web seminars later on about some various tools that Achieve has developed down in August. Archives. We've got more than 40 different web seminars archived around everything NGSS you could possibly think of. Also, the NSTA journals have new articles every month, and as an NSTA member, you can access all of the old issues, not only from the one you subscribe to, but from all the journals. So take a look at that. We also have some that are freely available and a bit listed on the Learning Center or in the hub. We have books galore in place about all sorts of different pieces with NGSS. There's an app for the standards as well. And we've got our area conferences coming up this fall in place that I hope you all can make it to your corner of the world. And with that, I pass things to Sue, who can do the formal shift and ending piece.
Thank you, Ted. And I'd like to go back again, and I know you guys are anxious for the survey, but I would like to, again, go back and give our presenters today, including Ted, a round of applause. And you find applause underneath your smiley face, which is underneath your name, and if you look up at my name, you'll notice I've got two hands clapping. So again, a round of applause for a phenomenal web seminar. It's just the beginning of a great series that's coming out. I encourage you to follow the links and get registered for additional web seminars. Okay, and with that, I'm going to go forward. And I'm going to thank the Carnegie Corporation of New York for sponsoring today's program. I'd also like to thank the administration of NSTA for their support of web seminars. And I'm going to conclude the program now and stop the recording.